All right, friends, here we go again. I started filming this one a little bit ago and ran into some technical difficulties, so here you go. Round two. All right, so this is question number 6 from the 2019 BC exam. Question number 6 is usually, not always, but usually a series question. The College Board mixes in all sorts of different ideas. Let's see what we have in this one. A function f has derivatives of all orders for all real numbers x. Having derivatives of all orders means that f prime exists everywhere, f double prime, f triple prime, f quadruple prime. All the derivatives you could ever possibly want to take will exist at all real numbers. This is something we sometimes call these curves smooth curves or infinitely differentiable curves. All these derivatives are going to exist. This is a really nice property that's going to allow us to do a lot. A portion of the graph of f is shown above, along with the line tangent to the graph of f at x equals 0. Selected derivatives of f at x equals 0 are given in the table above. So let's get the lay of the land here. So we've got the graph of f. We've got our tangent line. This is the tangent line to f at x equals 0. And then this table over here gives us values of the second derivative at x equals 0, the third derivative at x equals 0, and the fourth derivative at x equals 0. Let's look at part A. Write the third degree Taylor polynomial for f about x equals 0. So third degree, I usually like to write that as p sub 3. The third degree Taylor polynomial for f about x equals 0 is going to have the form f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x cubed. Okay, well, where do I get f of 0? I'm going to go to the graph of f. I'm going to look at the value of the function f at x equals 0, and I see that that's 3. Plus, now I need f prime of 0. Well, f prime, that means slope of the tangent line at x equals 0. How convenient. They gave me a tangent line to the graph of f at x equals 0. I need to find the slope. Well, the slope of a line I can do rise over run. I have 1 point. And if I go down 1, 2 spaces, and 1 to the right, I'll get another point on that same line. So my slope is negative 2. F prime of 0 is negative 2 times x. F double prime of 0, the value of the second derivative of f at x equals 0, well, that comes from the table. Second derivative, if I evaluate that at 0, I'm going to get 3. So 3 over 2 factorial times x squared plus the third derivative at 0. Third derivative evaluated at 0 is negative 23 over 2 over 3 factorial. I can clean this up to get p sub 3, the third degree Taylor polynomial for f centered at x equals 0 is 3 minus 2x. 3 over 2 factorial is the same as 3 halves. 3 factorial means 3 times 2 times 1, that's 6. Negative 23 over 2 divided by 6 is the same as negative 23 over 2 times 1/6, which is negative 23 over 12 x cubed. That's it. College Board awarded 1 point for these first 2 terms and another point for the last 2 terms for a grand total of 2 points. That's part A. That's all that you needed to do. Let's look at part B. In part B, we're asked to write the first 3 non-zero terms of the Maclaurin series for e to the x and then write the second degree Taylor polynomial for e to the x times f of x. Well, the Maclaurin series expansion for e to the x says e to the x is approximately 1 plus x squared over 2 factorial, x cubed over 3 factorial, and so on. The first three terms, or the first three non-zero terms, there's just going to be 1 plus x squared over 2 factorial. This is one of those things the College Board just expects that you know. Now, if we want to talk about e to the x times f of x, well, e to the x, right, this guy is approximately 1 plus x squared over 2 factorial, and so on, times f of x. Our work from before says that f of x is 3 minus 2x plus 3/2 x squared minus 23 over 12x cubed, and so on. What they want is the degree 2 expansion. Don't overthink this. We know the expansion for e to the x. We know the first part of the expansion for f of x. The degree 2 expansion is going to come from the multiplying of this infinite polynomial with this infinite polynomial. And before you freak out too much, we want the degree 2 expansion. So we are only looking for terms that will be degree 2 or less. Think about your multiplication. The 1 gets multiplied by the 3 with the negative 2x and with the 3/2 x squared. And yeah, the 1 would multiply with the negative 23 over 12x cubed, but that degree is too high. So I'm going to have 1 times 3 is 3. 1 times negative 2x, I'm going to have 1 times 3/2 x squared. I'm now going to multiply the x. X will multiply with the 3, that's okay. The x multiplies with negative 2x, that's okay. But x times 3/2 x squared is cubic, that's too big. So I'm going to also add in 3x minus 2x squared. Now before you think you're done, you also have to multiply the x squared over 2 factorial times 3 because that gives me a quadratic term. I don't multiply the x squared over 2 factorial times negative 2x because that's a cubic term. So the last term in my expansion will be 3 over 2 factorial x squared. All of these terms are degree 2 or less. That's what I'm looking for. You can simplify further if you'd like to. There's no need to save a little bit of time here. I'll tell you that the simplified answer, if you do it, is x squared plus x plus 3. I would not encourage you to do that. I'd say leave it alone. College Board awarded 1 point for the identification of the first 3 terms of e to the x and for getting these 3 terms here. So this is worth 2 points. I would expect most of you would be able to pick up at least the first point, maybe the second point as well. And for question number 6, being a series question, I think we're in a really good place so far. Let's keep going. Okay, part C says let h be the function defined by h of x is the integral from 0 to x of f of t dt. Use the Taylor polynomial found in part A to find I want an approximation for h of 1. Now let's talk about why it has to be an approximation. The exact value of h of 1 is what I would get if I integrated f of t dt from 0 to 1. Well, why can't I do that? Problem is, although I know what the graph of f looks like and I know information about f at different places, I don't have an equation. I don't have an analytic representation, so I can't do what I would normally want to do. But what I can say is that h of 1 is approximately what I'm going to get when I integrate my approximation from part A. My degree 3 Taylor polynomial was 3 minus 2x plus 3/2 x squared minus 23 over 12 x cubed. I want to integrate that with respect to x. That shouldn't be too bad. These are all polynomials. We use the power rule. The integral of 3 is 3x minus the integral of 2x, add 1 to the power, divide by the new power, that's x squared. Add 1 to the power here, you get x cubed. 3/2 divided by 3 is 1/2. To integrate x cubed, I'm going to get x to the 4th, add 1 to the power, divide by the new power, we're going to get negative 23 over 48. And now we evaluate from 0 to 1. That means all that you have to do is everywhere you see an x, plug in 1. You get 3 minus 1 plus 1/2 minus 23 over 48. Minus plug in 0, you get 0 minus 0 plus 0 minus 0. And there is no way I am going to bother simplifying this expression. They're all numbers. There's no need. So where did they award points? There was 1 point for coming up with the correct antiderivative, and there was 1 point for the correct evaluation, for a grand total of 2 points. And if you're keeping track, we are up to 6 points out of 9. We have 1 part left. Let's see what we've got here. In part D, they go on to say, it is known that the Maclaurin series for h converges to h of x for all real numbers x. Okay, let's keep going. It is also known that the individual terms of the series for h of 1 alternate in sign and decrease in absolute value to 0. So the individual terms for h of 1, the way I approximate h of 1, those terms, they alternate in sign and decrease in absolute value to 0. I am hoping that that is getting you to start thinking about something important. These are the conditions for the alternating series test. We'll come back to that in just a little bit. Use the alternating series error bound to show that the approximation found in part C differs from h of 1 by at most 0.45. Okay, what's going on here? It's known that the series for h converges to h of x for all real numbers x. Okay? It is also known that the individual terms for h of 1, the terms for h of 1, they alternate, meaning that they're going to be switching positive to negative, and then they decrease in absolute value to 0. Those two things together tell me that the alternating series test applies. And the alternating series test is the thing that says if I am using an approximation, if I'm using an approximation to get to the true value of the function, the error between, let's call this, the error is the difference between h of 1 and our approximation. Our approximation had this form 3 minus 1 plus 1/2 minus 23 over 48. That error is going to be less than the first term that I didn't include. And the first term that I didn't include in my approximation for h of 1 was the integral from 0 to 1. Well, think about what happened. We used, what did we use? We used our degree 3 Taylor polynomial. F of 0, f prime of 0 times x, f double prime of 0 over 2 factorial x squared, f triple prime over 0 over 3 factorial times x cubed. The only thing I didn't use, the first thing I didn't use is the degree 4 term. The degree 4 term is what I find by looking at the fourth derivative evaluated at 0, so 54, over 4 factorial times x to the fourth. That would be the first term in the degree 4 Taylor polynomial. My error is going to be less than that. Well, this, as ugly as this is a polynomial. To integrate it, I'm going to add 1 to the power, and I'm going to have 54 over 5 times 4 factorial. If you're not sure what happened, add 1 to the power, divide this fraction by that new power, and evaluate from 0 to 1. You're going to get 54 over 5 times 4 factorial times 1 to the 5th, which is 1, minus 0. That's 54 over, well, let's see, 5 times 4 factorial. 4 factorial is 4 times 3 times 2 times 1. That's 24. You get 54 over 120. And you might not see the significance of 54 over 120, but if you reduce this, you can reduce top and bottom by 6. You get 9 over 20. 9 over 20 as a decimal is 45 hundredths. The error is which is the difference between the true value and the approximation, is less than, strictly less than, this expression over here. That's what we were after. I think this is, whenever it comes to alternating series, error bound, Lagrange, it's always a little bit tricky. This is not the worst one I've ever seen. It could absolutely be a lot worse. But the conclusion is that the error, the absolute value of the error, has to be less than or possibly equal to 0.45. I guess I should have used less than or equal to back there. But that gets at what we wanted. College Board awarded 1 point for using the degree 4 term. Let's see, then they said uses, for use of the first omitted term of series of h of 1. Yeah. And then for the error bound. That's your third one. Let me look at that one more time. First point is uses the fourth degree term of the Maclaurin series for f. That's what we're doing here. Second is uses the first omitted term of the series for h of 1. Those sound like the exact same thing to me. And then the error bound. Okay. Quite honestly, I'm not sure where the second point comes in, but this is a grand total of 3 points. I would say parts A, B, and C are relatively, maybe not easy, but like the kinds of things I would expect. I would also expect part D, but I also know we don't get nearly enough time with the error bound. So good luck. I hope that was helpful. If not, send me an email and we'll chat about it. Thanks.